Hello, my name is Gary Pace. Um, I'm a professional engineer, CWI, out of Katy, Texas. This is going to shadow NCCER Basic Materials 34104-10. Um, it's going to cover paragraphs 4.0 structural steel and common shapes out of Boilermaker Level 1. A lot of the material you're going to read in here or see, um, because I'm kind of shadowing what they did. I took my material from alternative sources. So a lot of this is coming out of the U.S. Navy and open source materials and Army materials and things that are in the public domain. So it's going to cover the same material, but it's not going to be the exact same wording as in the book if you were following along with Boilermaker Level 1. So there's going to be a little bit of difference, but it's going to cover the same material. Little background, I spent 4 years on the USS Saratoga as a machinist mate, which dealing with boilers, machinist mates deal with boilers, feed pumps, steam turbines, all that kind of good stuff, heat exchangers. So I'm a licensed boiler operator in the state of Montana. Anyways, that's where we're going to cover. We're going to talk about basic materials in this YouTube video. Our learning objective here, we're going to talk about structural steel and common shapes. And we're also going to talk about cladding a little bit. These are all common themes for Boilermakers. You need to know what material that you're building a boiler out of. If you're coming from another industry, you need to have a basic vocabulary of structural steels and the common shapes utilized in boiler construction. You know, channels, angle irons, plate, bar, things like this. So we're going to cover that, and we're going to get into cladding. Okay, I know it gets tedious. I include one of these in about every other presentation I do, but I guess I just want to spread the wealth. Acknowledgments, I poach a lot of this material from the Nuclear Regulatory Commission, Introduction to Welding Technology and Code courses, ML 12157A587. It's a good starting point. Can teach the Canadian deuterium uranium people. HTTPS, I'm not going to read that web page. You guys can figure it out, the can do stuff. The U.S. Army's also got a pretty good, it's old, but it covers a lot of material. TM 9-237, Welding Theory and Application, is a good place to find some high quality welding information. None of it's changed over the last 50 years, but anyways, that's why I always include this, is because there might be somebody out there that's looking for some free material, doesn't want to pay for a book, and you want some good high quality welding material. This is it. Structural steel and common shapes. Structural steel is a category of steel used for making construction materials in a variety of shapes. Many structural steel shapes take the form of an elongated beam having a profile of a specific cross section. Structural steel shapes, sizes, chemical compositions, mechanical properties such as strengths, storage practices, etc., are regulated by standards in most industrialized countries. So basically, this is telling us that most countries have structural steel shapes. So a common I-beam size in the United States might not be a common size in Europe or Japan or China. So there's differences there. You know, the chemical composition of a steel in the United States might not be exactly the same as one in China, but they might be comparable. So we're going to talk about that, and we're not going to get into the standards, but we might touch on them a little bit. 4.1, structural steel classifications. So we're going to talk about plate, sheet, bars, angles, channels, beams, steel pipes, and tubing. Most of this material I got out of the Steelworker manual. It's a U.S. Navy manual. Boilermaker one in chief, I think, is a one that was a U.S. Navy manual back in the 1960s. Boiler Technician 3 and 2, and a couple other military manuals. A U.S. Army manual is also where I poached a lot of this material. But anyways, This is the material we're going to cover, and we'll go from there. Steel plate. Here's some pictures of some steel plate. Steel plate is a flat rolled product from slabs or ingots of greater thickness than sheet or strip. Plates are between an 1/8 inch and 8 inches thick and used for large welded pipes, shipbuilding, construction, major works, and boilers. So anything less than an 1/8 of an inch is considered to be sheet or strip. And if it's an 1/8 to 8 inches thick, it's considered to be plate. So steel plate is anything between an 1/8 and 8 inches thick, and it's flat like this. It's a plate. So odds are in your career you're going to see a lot of steel plate if you're making boilers. Steel plate is a structural shape whose cross section is in the form of a flat rectangle. Generally, a main point to remember about the plate is that it has a width greater than 8 inches and a thickness greater than an 1/8 of an inch or greater. Plates are generally used as connections between other structural members or as component parts of built-up structural members. Plates cut to specific sizes may be obtained in widths ranging from 8 inches to 120 inches or more, and in various thicknesses. The edges of these plates may be cut by shears, a sheared plate, or be rolled square by universal mill plates. Steel sheet, a flat rolled product over 12 inches in width and of less thickness than a plate, usually less than an 1/8 of an inch, is considered to be steel sheet. So generally considered. So you could call it, that 1/8, quarter inch range. It's kind of a gray zone, but generally anything less than an 1/8 is considered to be steel sheet. When you're welding to AWS D1.1, anything less than an 1/8 goes into D1.3, which is structural sheet steel. So that's kind of where my version of the cutoff comes across, at an 1/8 of an inch. Here's an I-beam. It's a girder that has the shape of an eye when viewed in the section view. So if you take a section view of it, if you look at it from the end, it looks like the letter I. Hence, it's an I-beam. When we're dealing with beams, we have two general types that we deal with. We have a wide flange and we've got an I-beam. So there's a couple of subtle differences in them. You can see that the shape is different. The wide flange looks more like an H if you turned it over. And the I-beam has a subtle difference there. You can see it's a little bit more curved and sloped, I guess, would be the my description of it. So you can see the wide flange is on the left-hand side, and the right-hand side is an I-beam. Here's another view you can take a look at, and you can see the wide flange, which they call a W shape, and then on the far right-hand side, C, we've got the I-beam. You can see it's a little different shape than the wide flange. They both have different structural capacities, and that's outside the scope of what I'm going to talk about here. It's more of an engineering thing, but you can see there's different shapes here. That's what I'm trying to get across, is that just because somebody says it's a beam, it could be a wide flange or it could be an I-beam, depending on what you're building, where, how, why, and who designed it, and what the structural constraints of the structure are. So a little quick vocabulary when we're talking about beams. The wide flange I-beam W shape is a structural steel shape with I or an H form, depending on which way you're looking at it. The top and bottom plates of an I-beam are named flanges, and the vertical plate which connects the flanges is named the web. So you got a web and a flange. Pretty useful vocabulary, because this is how we measure it to check and see what exact shape it is, and what material we're working with as far as the size of the material. Wide flange I-beam, a W shape. Wide flange I-beams are most commonly used structural shape in construction works. Materials of wide flange beams are generally structural steels such as A36, A572, A588, and A992. The designation of the wide flange I-beam gives information about the width and width per unit length. An example would be a W12 by 96 means 12 inches depth and 96 pounds per foot per unit length. The depth values are generally approximate. So for a W12 by 96, the actual depth value is 12.71. So when we call out a beam size, and I'm going to pick a mythological one, let's say I call out a W times 112, a W14 times 112. That means my depth is going to be 14 inches, and my length, every foot of that material is going to weigh 114 pounds. The one we called out here is a W12 by 96. It means it's 12 inches deep, more or less, and it's 96 inches or 96 pounds per foot in unit length. So if you had 10 feet of that material, you'd have 960 pounds of steel. So it's a pretty good way to, figure out the weight of a material. So, but that's how we size wide flanges. That's the nomenclature for beams. A W12 by 96, a W36 by 950, whatever. There's whole tables of this, which we will discuss in the next slide. Here you can see we've got the width of the web, the flange thickness, the thickness of the web, we've got the depth, and then you got the radius of the fillet. These are the definitions when we're dealing with I-beams and wide flange I-beams in general. So here's some W-shaped dimensions that we've got. These are the smaller guys. You can see that it'll give you the dimensions of the thickness of the web, the width and the thickness of the flange, distances on top to bottom. So it tells you the general sizes. There's whole tables of these sizes because we're dealing with 10-inch beams here or 10-inch flanges. Here's some more of that the table. We're dealing with 36s, 33s, some bigger materials, right? So from top to bottom of that I-beam or wide flange beam, we're talking about a W36 by 231 on the top of that bottom row of numbers, or you could have a W36 by 800. So that would mean that it's 36 inches deep and it's got a weight of 800 pounds for every foot of material you have. So that's a pretty big beam. Here we've got an angle, or commonly known as an angle iron. An angle is a structural shape whose cross-section resembles the letter L. Two types are commonly used, an equal leg angle and an unequal angle. The angle is identified by the dimensions and thickness of its legs. For example, an angle 6 inches by 4 inches by ½ inch. The dimensions of the legs should be obtained by the measuring along the outside backs of the legs. So a 6 inch by 4 inch by ½ inch means that our material would be a ½ inch thick, and one leg would be 6 inches and the other would be 4. That wouldn't be an equal leg angle. That would be an unequal leg. Or you could have a 2 by 2 by ½ inch. That means you'd have 2 inches by 2 inches by ½ inch material. Okay, here we've got the dimensions on an angle iron. You can see where we've got the height and the width and the thickness. So if we had a 2 inch by 2 inch by ½ inch or ½ inch thick material, the height of that material would be 2 inches, the width would be 2 inches, and then the thickness would be ½ inch. Or you could have a 4 by 2. You could have, a width of 4 inches by a height of 2 inches and a thickness of, a quarter or 3/8, depending on what you needed as far as a material. This picture you can see we've got an equal angle and an unequal angle. So an equal angle would be a 4 by 4 by 3/8 inch. Your legs are equal. And the other one looks more like an L. So you might have a 4 by 2 or a 3 by 4 or a 1 by 2, just depending on what size you needed. So there's a lot of different variations on angle irons. Like most other structural materials, you've got different lengths and sizes. So this one gives you, because this material is measured in size, 3 by 2 by 3/16 or 3 by 2 by a quarter or 3 by 2 by 5/16. There's no designation there that tells you how much a foot of this stuff weighs. So they have tables that will tell you how much a foot of it weighs, how much 20 pounds of it weighs, how much a 40-pound stick weighs. The C-shape American Standard Channel has a cross-section somewhat similar to the letter C. It is especially useful in locations where a single flat face with outstanding flanges on one side is required. The C-shape is not very efficient for beam or columns when used alone. However, efficient buildup of members may be constructed of channels assembled together with other structural shapes and connected by rivets or welds. So if you need a piece and you just need a flat side on one side, this is your piece. It's kind of like an I-beam cut down the middle. I've seen where people have put two of these together back to back to get build a beam or a column, using these guys instead of a I-beam or a wide flange. Here's a good look at some channels and also the dimensions in which we measure channels. We've got thicknesses, A, which would be the width, and B would be the height. So pretty common building material and structural components out of steel and carbon steels and stainless steels. Channel dimensions. Here you can see we've got, I outlined on the charts, you can get there's a lot of literature out there. Everybody that makes these channels and wide flanges and angle irons, they all have little books. It's not really a book. It's more like a thick pamphlet or a small book, but it holds all this information. So it's going to tell you, like this one you can see in red, I've outlined the 6-inch. So it's going to tell you the weight per foot, the thickness of the web, which would be dimension C. It tells us our depth, which would be dimension A, and then it's also going to tell us the width of our flange in B. So you can see these aren't all exactly the same. So, but it tells you for a 6-inch channel, the different depths and weights and other dimensions, thicknesses, etc. Structural tubing. Structural tubing is used in more high-stress, long-term corrosive applications such as infrastructure, roads, bridges, buildings, construction and construction equipment, sign supports, drilling and underwater platforms, and roll cages. Here we're showing some structural tubing. The one on the right would be square, and then there's some rectangular and other shapes on the left side of the picture on the left. A lot of times you use structural tubing. We've all seen it. You can make different skids and supports and stairs, and there's all kinds of different uses for structural tubing. Just depends on what the engineer calls out. Big structural tubing, a lot of times you'll see holding up a sign next to the McDonald's or Burger King or some big situation like that, outside the mall or whatever. So that's a lot of the uses of structural tubing, where you don't need a channel or an angle iron, but you'd need something that was more fully enclosed, maybe to keep the the moisture from getting in a crevice or something. But this is what structural tubing is. Here you can see a lot of different shapes and sizes of structural tubing. I mean, it's all kinds of shapes, sizes, flavors, chemical compositions, a lot of different directions you can go with structural tubing. Structural tubing. Square and rectangular tubing is measured by dimensions and wall thickness. So you're going to tell them it's a 4-inch by 6-inch piece and I need a wall thickness of 1/2 inch. Or I need a 2 by 2 by 1/4 or 3 by 3 by 1/2 or whatever the dimensions are. But you're going to give them the wall, the length of each side in inches, and then you're going to give them the thickness of the wall, which on this would be dimension C. And as I said before, all these materials, if you're going to go to a supplier to get tubing or any kind of other steels, they usually have a book that they'll give you. You know, most designers have a copy of these books. So then it tells them, you know, the sizes and the weights of the structural tubing and what they need to use, the wall thicknesses, things like that. A lot of useful information. So I think this is more or less used on the other side, the design side of things. But you can generally, tubing is called out in dimensions and weight, or not weight, wall thickness. So 6 by 6 by 180 wall thickness would be how you call it out, or 6 by 6 by 1/2 inch. So obviously the thicker the wall, the heavier the material is going to be, and the more expensive, because they're basically just charging you by the weight. So, you know, a 6 by 6 by 1/2 inch wall is going to be significantly more expensive than a 6 by 6 by 180 wall thickness. And most of this stuff is going to be determined by the engineers or the people designing the component or the structure. They're going to decide how much, strength in compression and tension and flexing and whatever that they're going to need for the component being built. So that's why we have these different sizes. There's different applications, different load situations, different load configurations. But it gets back to, if you ever need to look this up, there's places you can find this on the internet. And there's also, they have a lot of little books that, will tell you this information so that you don't sound like an idiot when you order this stuff. You can, I need a 20-foot piece of 6 by 6 by, 313 or whatever size. Okay, we're going to have to get a definition out of the way. We're going to have to talk about nominal pipe size. Nominal pipe size, NPS, is a North American set of standard sizes for pipes used for high or low pressure temperatures. Nominal refers to a pipe in non-specific terms and identifies the diameter of the hole with a non-dimensional number. For example, 2-inch nominal pipe, steel pipe, consists of many varieties of steel pipe, with the only criterion being a 2.375 inch outside diameter. Specific pipe is identified by pipe diameter and another non-dimensional number for wall thickness, referred to as a schedule. For example, 2-inch diameter, schedule 40. So pipe, the outside diameter is going to be the same when we're talking about nominal pipe size. So all 2-inch pipe is going to have a 2.375 outside diameter. The wall thickness is going to be the difference. And wall thicknesses are called out by schedules. Schedule 10, Schedule 20, Schedule 40, Schedule 80, Schedule XXS. So you have different pipe schedules. And of course, there's a little chart that you can find all this information on. But when you start talking about pipe, they talk about schedules. So if somebody says 2-inch Schedule 40, they're just talking about 2-inch diameter pipe, and it's got a specific wall thickness for whatever Schedule 40 is for that wall size. So kind of confusing, but once you kind of understand how the system works, it makes it a little easier to digest. So as I said before, we're going to talk about we're going to discuss the schedule and then the outside diameter. Those are the two things we use. And it's a nominal size. So we've got the schedule, which is the thickness, and then the outside diameter is the nominal pipe size. So even though it says 2-inch nominal pipe size, it's 2.375. And then there's going to be a variation on the thickness depending on which schedule we use. The bigger the number, generally the heavier the schedule thickness, the thickness of the wall. We've also got the definition nominal, a quantity or a dimension stated or expressly but not necessarily corresponding to an exact or real value. So nominal pipe size of 2 inches is not exactly 2 inches. When we're dealing with pipe, you've got a nominal pipe size. So you could have 2-inch pipe is not really 2 inches in outside diameter. Nominal is saying in the ballpark. Nominal is close enough, we're not getting scientific with it. So here's another view of, what we're talking about as dimensions. We've got outside diameter, we've got wall thickness, which is the schedule. Say that again for the sake of redundancy. Wall thickness is the schedule. How thick the wall of the pipe is called a schedule. And then we've got the inside diameter, or ID, and we generally don't worry about that when we're talking about pipe sizes. Okay, with pipe tolerances, not every pipe is perfectly round and has the same wall thickness on each side. You're shooting for that, but you can have differences in the wall thickness. So they give them tolerances. So one side can be off a little more than the other. You might have a thick side and you might have a thin side. Depending on which pipe standard you're working to, you can, it might be within the tolerances. The OD in pipe can vary as well as the wall thickness. These tolerances can vary, but should be a specification. Also, this is the reason that many times that pipe fitters and boilermakers will machine bevel pieces of pipe before they weld them together. So to get a good fit, they need to machine it. So you'll chew out a bunch of material out of the places where you don't need that extra material, and the welder a lot of times will, when he makes the weld, he'll blend it in or make a smoother transition. But a lot of times you'll get pipe that doesn't match up, or it's not perfectly round, so you can have a lot of problems. And if you're going into the boilermaker or pipe fitter trade, you're going to run into these issues with different pipe sizes. And depending on which pipe mill you got it from, some pipe, it's like buying cars. Some cars are better than others. Some pipe mills produce substandard pipe or dirty steel or whatever. So there's a lot of issues you can run into in regards to pipe tolerances. Here's a pipe schedule chart. Like I said, you can find these on the internet. It'll tell you the weights and wall thicknesses and the outside diameters of the pipes that you're using. So here I've circled a 6-inch, and we look at the top and we go to schedule 40 and we go down, and the outside diameter for our 6-inch pipe is going to be 6625, right? Well, and that's a nominal. It's not exactly 6-inch. It's a little over 6.5. So it's 6 5/8, I guess, is the actual outside diameter of that pipe. But we say it's a 6-inch pipe, nominal pipe size. So then the wall thickness is going to be 0.280. That's the wall thickness for schedule 40 6-inch pipe. And then it's going to tell you the weight per foot. Well, if we bump over to schedule 80 is going to be a significantly thicker wall. So it's going to be 0.432. And then you can notice for like the smaller sizes, the schedule 80 wall thickness can range from, 0.095 for schedule 80 on the 1/8 inch pipe, all the way up to 12 inch is going to have 0.5 inch wall thickness for schedule 80. So the schedule depends on what your nominal pipe size is for wall thickness. Just because it's schedule 80 or schedule 40 doesn't mean it's going to be the same for 4-inch pipe as it is for 6-inch pipe. So that's why we got the little pipe charts. Keep track of this stuff. It's good stuff to know. Get one of these and put it in your toolbox. Okay, so here's where we're going to get things confusing for everybody involved. Pipe versus tube. Generally, tubing is measured with the outside diameter, but it's exact. It's not a nominal size. It's exact. Whereas 1.5-inch pipe, we can see here in this example, it's got a 1.9-inch OD, and we're saying it's a 1/2-inch pipe. Well, if we're using 1/2-inch tubing, 1.5-inch tubing, we've got an exact OD. It is 1.5 inches OD. So tube is generally structural, measured by exact OD, outside diameter, and pipe is for fluids and vessels for the most part. And not to say you can't use tubing for other stuff. It's measured by nominal OD. Nominal, once again, means more or less, general ballpark. So this is what we need to take into account when we're talking about pipe versus tubing. Cladding and surface modifications are extensively used in fabrication of pressure vessels and other fluid systems. It essentially involves adding a layer of a different material to a component surface. The cladding of pressure vessel internals to improve erosion, corrosion, and wear resistance. It builds up a buffer layer for dissimilar metal welds, and fusion welding based processes, i.e. various arc welding processes, GTAW, SMAW, GMAW, SAW, are typically used for cladding in today's pressure vessels. So pressure vessels and valves, pipes, there's a lot of times that you're going to need a certain corrosion resistance or material properties to keep a fluid from corroding or destroying your metal. So if you're going to make something out of, a nickel alloy, it would be super, super expensive. So sometimes we'll clad it. We'll put a layer of, let's say, nickel or stainless steel on the inside of a boiler or pressure vessel or whatever. And then the outside will be carbon steel. Carbon steel's cheap. It's pretty strong. It's easy to work with. So we'll do what's called cladding. So you put a thin layer or a specific layer, thickness of a layer of a material that's got good erosion or corrosion resistance on the inside of a pipe or a valve or a pressure vessel or a heat exchanger or whatever, and you're using it as you've got the outer material, which is the strength generally, and then the inside, the cladding, is the corrosion resistance. Here would be an example of cladding where we would have some 316, so use like 316 stainless steel on top of a carbon steel substrate or base material. Let's say we're pumping ketchup through some pressure vessel, and it's too expensive to build the whole pressure vessel out of 316 stainless steel. And this is a hypothetical situation. I don't know where you would use this, but in oil and gas, a lot of times they'll clad carbon steel valves because they're cheap with a stainless steel or an Inconel or a Hastelloy, these nickel-based alloys, because to get that valve made in one of those alloys or materials would just be super cost prohibitive. So you can just go in there and clad it. So here we've got a situation where hypothetically we're putting 316 stainless steel over a carbon steel. Whether or not that's actually used, I don't know, but that would be an example. Brief history of cladding. Cladding of carbon steel and low alloy steels with corrosion resistant materials has been performed commercially since the early 1930s. Gas and arc welding techniques were used to overlay backing steels with corrosion resistant metals. Automated processes were preferred and were commonly used in the early 1950s. Here's a couple of, processes. We've got, gas tungsten arc welding in that upper right hand um, sketch or schematic where you're using gas tungsten arc welding and you're just cladding it with, whatever corrosion resistant material you need. I used to work for an outfit and we did here in Houston, and we do a lot of cladding on putting nickel alloys and stainless steel type alloys on the inside of valves. We'd build up this clad material and then send it off to a machine shop, and then they'd machine it down and make everything happy. Um, and then on the other side we've got submerged arc. Submerged arc, if you've never dealt with it, is a pretty big process. So this would be this is not for little work. This would be for just puking metal on there where you really need a lot of material and a higher deposition rate, and you need to, let's say you're cladding a vessel that's 20 feet in diameter. If you're going to do it with TIG welding, it's going to take a substantially greater amount of time than it would use a submerged arc. And this says it's a 6-wire submerged arc. So you got 6 wires pumping, clad material onto the corrosion resistant material onto the base material. Here's a couple pictures. You can see, I don't know what any of these components really are. I got them out of a Oak Ridge National Labs. You can see this component where they've clad the outside on the far left side. They've got they're building it up and putting some cladding on there. You can see in the middle picture they're using a submerged arc welding head, and that's about a 10-foot diameter piece of, I don't know what, pipe or a pressure vessel, some kind of digester. I got no clue as to what it is. There was no caption with it. But anyways, you can see it's a big piece, and they got it on those rollers, and they're just putting metal in there. They're cladding the inside of it. And then generally when we qualify a cladding procedure, we'll make a test plate, and you'll put the cladding on, and then you'll send it out for bend tests to make sure the mechanical properties of the clad material are the same as the base material. So it doesn't, if it's flexing or bending or whatever, that it's not going to come apart, that you're not going to have issues. It's not going to peel off or, give some corrosion path to the fluid that you're trying to keep from corroding everything. So those are some side bend tests on a nickel clad on stainless steel 316H. Okay, here we've got explosive cladding. I couldn't end on, just cladding alone. I needed to talk about explosive cladding. Whether or not you ever run into an explosive clad material or not, I don't know, but I thought it was pretty cool. I used to deal with some explosively bonded clad material where they'd take, stainless steel and aluminum, and they'd, use an explosive charge to get the two materials to bond. So here you've got your cladding, your clad material that you want to be stuck to the base plate, and then they light this thing off, and as it goes, it forces the two materials together. There's a pretty good YouTube video on this, Dirty Jobs or How It Was Made or whatever. If you do a Google search on YouTube for explosive cladding, it's kind of a neat one. They bury this stuff. They go in this cave in West Virginia or Pennsylvania, and they, touch off this explosion, and it bonds the two materials together. They have all this explosive material on it. It's pretty cool. So, but yeah, you don't have to just, cladding isn't just welded material, putting a layer of weld material on something. It can also be, you put one sheet on and then you clad it with an explosive bond. Summary. Okay, we covered structural steel and common shapes, and we also talked about cladding. With the structural steel shapes, we talked about I-beams and tubing and nominal wall thicknesses and pipe schedules. There's a lot of material there to digest, but if you're going to be a boilermaker or a pipe fitter, You're going to need that information so you can talk to your coworkers and understand instructions. We talked about cladding, a couple of different types of cladding. Not so much where it's used, but that it does exist. And it just involves basically putting down a layer of stainless steel onto a carbon steel, or let's say a nickel alloy onto a stainless steel. There's a number of different variations in chemical or metallurgical directions you can go with cladding, depending on what is flowing through your pipe valve system. So, my name's Gary Pace. I'm a PE CWI out of Katy, Texas. If you want to track me down, there's how you can find me. You got any questions, comments? Like the video, didn't like it? Maybe you got a suggestion for another video? Let me know. Thanks. Take care. GP out.